Hello everyone, this is separation processes course. Today our topic is liquid extraction. Again, liquid extraction. Starting by the title, we can see that it consists of two parts, liquid and extraction. So first, what do we mean by liquid? Then what do we mean by extraction? Okay. So liquid, it's a vase. It's a vase. Uh, that's a type of fluids. No fluids. Any fluid could be gas or vapor or liquid. Okay. So our focus in this chapter is only on liquids. It's not like distillation where you see liquid and vapor. No. For extraction, for this chapter, we are going to focus only on the type of extraction called liquid extraction. So it involves only liquid phase. Okay. The question here: does liquid phase is only one phase always? The answer is no. You can have two different liquid phases. So what's the meaning of a vase? What's the meaning of vase? So vase is just a homogeneous homogeneous matter. Homogeneous matter. What do you mean by homogeneous? Homogeneous means it consists of three things: constant temperature, constant pressure, and constant composition. Composition or concentration. To better illustrate the concept of what do we mean by a vase and how we can have two vases and both are liquid, we can draw an analogy here with a very famous example. That's suppose you have a container, okay, and this container has you add to it, for example, water, H2O, and you add to it oil, okay. Then what happens inside this container? You're gonna see something like this. You're gonna see, I don't know, something like this, mixed oil and H2O mixture. Then if you wait some time and then go back to the container and see what's inside this container, you will find something like this. You will find that oil goes up and water goes down after some time. In other words, after you allow the equilibrium to be achieved. What do you mean by equilibrium? Equilibrium is a static state where everyone, either H2O or oil, know his place, know where to sit. So H2O sit down and oil sit up. The question here is why? Why H2O sit down and oil sit up? The answer is it's due to the difference in density, because H2O usually has a higher density than oil. Okay, that's why it sits down, because it has a higher density. Okay, so another question here to be asked is how many vases we have inside this system, oil and water system. How many vases? The answer here, let's back to the definition of what a vase is. As we said, a vase is a matter that has constant temperature, pressure, and composition throughout. Okay, so if we look at this system, suppose for example that the temperature in all of the container, let's say 25 degrees C ambient temperature and 1 atmosphere ambient pressure. Let's suppose this is the temperature and the pressure. So far, let's say, and now we have the same temperature and same pressure throughout the whole container. So far, we have only one vase. We have only one vase, which is liquid vase. Okay, but now let's see the third restriction here. The third restriction says that in order to have one vase, you need to have the same composition everywhere, the same composition and the same chemical makeup. Okay, but if we look at this container, we will find that the composition here at this point is different than the composition here at this point. Why is that? Because let's say this is point 1 and this is point 2. At point 1, everything is oil, almost. Maybe you can have some traces, some small amounts of water, but mainly at point 1, this is oil. But at point 2, this is mainly water. You can have some traces of oil, but mainly it is what? It is water. So you can see here that we violate the third restriction. Here we have a different composition, which is mainly oil, and there we have different composition, which is mainly water. So we can consider each of these as one vase. Each of these. In other words, in this system we have two vases. One vase that contains mainly oil, another vase that contains mainly H2O, water. Okay? So you can see here we still have liquid vase. It's a liquid state. Let's say, to not confuse you, let's say it is liquid state. So we still have liquid state. Oil is liquid and H2O is liquid, but we have two vases. Why we have two vases? Because we have a contrast in the composition, the chemical makeup. That's why we can say in this system we have two vases. One vase is oil mainly and the other vase is H2O mainly. Okay? And in between these vases we have a vase boundary or vase interface. Here, in between these two vases, we have a vase boundary. A vase boundary is something in between the two vases. This is we call vase boundary, okay, or vase interface. Okay, so this is the meaning of liquid-liquid. This is how we can have two liquids that are in two different vases, because of the contrast and composition. Okay, so let's back to the title. This is liquid-liquid, so we are talking only about two liquid vases, not like distillation where we have liquid and vapor. No, here we have liquid and liquid, but both are at different vases. Okay, liquid vase 1 and liquid vase 2. Okay, extraction. What do we mean by extraction? It seems like a new separation technique. It is not distillation. We finished with distillation, but now it is a new separation technique called extraction. So what do we mean by this separation technique? What do we mean by extraction? This is our topic today. Extraction, in simple words, it is like when you have, again we are dealing only with liquid, no vapor here, only liquid. Extraction, it's like when you have, suppose you have a mixture between, let's say, component A and component C. Okay, let's suppose we have this mixture and we want to separate these two components. We want to separate A from C. Okay, so what you can do, you can take this mixture, and feed it to a distillation column and get your distillate and waste streams, so you can separate. It depends on which one is more volatile, so you can get this A. If it is more volatile, you can get it in the distillate, and you can get this C. If it is heavier, you can get it in the waste, or vice versa. It depends on the relative volatility, as we discussed before in the distillation. Okay, but the question here, why do we need extraction sometimes? Why do we need extraction? Why do we feel the need to develop a new technique to separate components rather than distillation? The question here is that there are too many reasons. It's not only one reason, there are too many reasons. Some of these reasons to skip distillation and go for extraction is that sometimes you have these two components, let's say A and C, they are very close in boiling point. They are very close in boiling point. In other words, they can form azeotrope, and as you know, azeotrope is bad for distillation because it makes it more difficult to separate these two components. To illustrate this, it is like you will get, if you use makeup and tele method, you will get something like this. What you have, this is the 45-degree line. You will get a tight equilibrium curve, very tight, that's very close to the 45. Why? Because this equilibrium curve, as the relative, or let's say at azeotrope, if you have azeotrope, you will have very low relative volatility. That's very close to 1. In other words, it's very close to the 45-degree line. Okay? And as this relative volatility increase, you will get bigger and bigger curves. Okay, so let's say in this blue curve represents equilibrium curve for azeotrope. So what happens after you draw the operating lines? As we know before, we draw operating lines and the feed line and WQ line and another operating line. So what will happen? You will get too many number of stages. See, because it is tight. 1, 2, 3, 4, 5, 6, 7, 8, 9. Very tight. Then you can get, I don't know, 20, 30 trays. You need too many trays. Rather than suppose if you have a high relative volatility, in other words, high relative volatility means high difference in the boiling point. So you will get lower number of trays. See, like focus on this curve, for example. So let's start here. We get 1, 2, and that's it. Only 2 stages. So you can see that the higher the relative volatility, in other words, the higher the difference in boiling point, the easier the separation by distillation is, and vice versa. The lower the relative volatility, the lower the difference in the boiling point between the two components, the more difficult the separation by distillation is, because you will need too many stages. Okay, you need too many stages. In other words, you need very tall column. Very tall column means extra money needed. So sometimes separation by distillation is not feasible. It's not good. So this is one case where you have the two components are very close in boiling point. For example, one of these components boil at 45 degrees C and the other boil at 48 degrees C boiling point. These are very close, so separation by distillation looks to be not feasible. Okay. Another situation, another reason, for example, is, remember, in distillation we need what? We need a reboiler here. A reboiler where you heat and then get this oil up back to your column. You need this reboiler, and as you know, this reboiler will increase what? This reboiler will increase temperature. Okay, this reboiler will increase the temperature. What happens, some components, for example, let's say our components here in this example A and C, these components, sometimes what happens, at high temperature you initiate other chemical reactions. So for example, at this high temperature of the reboiler, A will react with C to form another component. I don't know, for example, D, just as a name. So, and this reaction only activated at this high temperature. So this is bad. You are losing your components. You are losing your components and you are forming this third component that maybe you don't need it. You don't want it. So in this case, separation by distillation is not good. Separation by distillation is not good, and you need to look for an alternative process. Okay, so this is just an example of typical reasons to go for to go for another separation technique rather than the most fundamental famous separation technique, which is distillation. Okay. Uh, okay. So one of these alternatives that we can go for is extraction. We can go for extraction, especially if you have liquid vases, liquid extraction. So again, it begs the question here, what's the meaning of extraction? What's the meaning of extraction? As you might think, the first thing that may come to your mind is that in extraction, we don't need a reboiler. Okay, why? Because we said, and sometimes we avoid distillation because of this reboiler that has a high temperature that initiate another chemical reactions. Okay, so this is one thing that comes in your mind. The other thing that may come to your mind is that separation by extraction is independent on boiling point. It does not depend on the difference in boiling point. So it is not like distillation. It's a different separation technique. Okay? No matter, it doesn't matter whether you have a close boiling point components or and they are far away from each other in boiling point, so it doesn't matter. Okay, so again, what extraction is? Extraction, simply, in a simple words, it is like when you have, suppose you have again this mixture that consists of A and C. Okay, so what you do, you mix this mixture, with a solvent. Let's say this solvent, let's call it B, for example. Let's call it B. So you mix this mixture. You want to separate, for example, A from C. So you take this mixture, A and C, and mix it with the solvent B. Okay, but this solvent has some conditions, some restrictions. The first thing, suppose you want to separate this A. You want to take this A out. You want to separate it. Okay, so you need to choose a solvent that somehow chemically attract this A, and to some degree do not attract this C. Okay, to better illustrate the concept, let's back to our example of oil and water. Okay, let's back to our example. What do you think? Which is easier to dissolve NaCl, which is salt, in water or in oil? What do you think? Which one is easier? Of course, to dissolve it in water. Okay, so you make this salty water, like seawater. Seawater is a salty water, right? Okay. Okay. So, but is it easy to mix, to dissolve H2O in oil? As we see before, it is not easy, because later you will get this layer that where you here have this water and there you have oil. Okay, so we can say that we can say that water dissolve in ACl easy. Okay, so we can call this water B, solvent, for example. Okay, and the solute, which is NaCl, we can call it A. And let's call oil, for example, C. So now, suppose you have a mixture of NaCl and oil. You have, again, this is A and C. As we said, A represent NaCl, salt. C represent oil. Okay? Let's say you are interested to take this A, which is the salt, out. You want to separate it. So what you will do, you can mix it with water, H2O, water, which is B. We give it a symbol B. So this water, which is the solvent, will chemically attract this A and will not attract C. Why? And as we said, oil and water usually forms these two vases. They do not mix after some time. If you allow some time for the equilibrium to be reached, you will get two vases of oil and water. Okay? So, what happens after you mix these two? B will take this A. B and A now come together, and then you're left with this C. Okay, to some degree. It is not 100%. Yeah, for example, you can have, I don't know, 0.1%, for example, A here, and percent of B there, but mainly you have C. And mainly you have most of the A is attracted by the solvent B. Okay, which is now good. Separation is achieved. You separate A from C. So you have this almost pure C. It's not 100% pure C, but almost pure C. And the rest B and A, which is another mixture that, for example, maybe it is good for distillation to separate. So you can take, for example, this BA. You can take, for example, this BA and feed it to a distillation column, and then you get your A and your B, for example, by distillation. So maybe this mixture is better to separate by distillation. So it's like steps. Usually extraction is not alone. Usually you have this extraction and then you have distillation. Okay, then what you do, you can take this B, which is your solvent, back, recycle it back. You can take it back and recycle and use it again and again with a new feed of A and C. Then B takes this A, and then you take BA, feed it to distillation, you separate A from B, and then recycle B and use it again and again. So this is how things go in real industry. But again, our focus here is only on extraction. In this chapter, we are going to focus only on this step, which is extraction. So how extraction takes place. This is our focus in this chapter. Okay. So before we move on, let's first agree on the symbols. So let's say components. In extraction, we have 3 components. It's not like distillation. If you remember, in distillation, when we talk about distillation, we can have binary mixture, or we can have multi-component mixture, right? And as we said before, for binary mixture, we can use May-Kaptile method or Ponchon-Savarite method to analyze the distillation column in multi-stage, in not multi-stage, sorry, in multi-components. We can rely on, we cannot rely on graphical solution. We can rely on approximate solution like FUG method, Beninsky Underwood, Gilliland correlations, or if it is single for multi-stage distillation, and if it is single stage distillation, we can use that Rutherford race equation to that's what we have talked about before. But now the story is different when it comes to extraction. Mainly for simplicity, we are going to focus and deal with three components. Three components. So it is not binary system where you have A and B. In distillation, binary you have A and B. No. Here in extraction you have three components. In other words, we call it ternary system, not binary, ternary. Ternary system. You have this ternary system. What do we mean by ternary? Ternary means three. It is like binary. Binary means two, ternary means three. So we are going to deal with the three components. So let's give them as symbols, just to agree on the symbols, to not confuse you later. So let's agree from the beginning on the symbols. Okay? So let's go back to our example, which is oil, NaCl, salt, and H2O, water. So, as we said before, in this case, NaCl is the solute, and H2O is a solvent. This is the solvent that will attract this NaCl. It will attract it. Okay, and this oil, we call it that. Remember, so that's again to not confuse you. Remember, initially we have this oil and NaCl mixture. Okay, then we add the solvent, which is water. We add it, then the result is that water attract this NaCl, attract the salt, and then we left with almost pure oil. Okay, so NaCl that to be attracted is called solute. The component that will attract this solute is called the solvent. The component that holds the solute initially is called the carrier. So again, solute is to be extracted, to be taken. The solvent that will take this solute later is called solvent. The component that has the solute initially before extraction process is called carrier. Okay. Oil here in this case is considered to be the carrier from carry, like play, player, carry, carrier. Okay. So let's agree on the symbols. So we have a carrier, and this carrier has the solute initially, and we have the solvent that will attract that solute. Okay, so let's agree on the symbols. The carrier C, we are going to call it, or to give it a symbol, C. The solute, we are going to give it a symbol A. The solvent, we are going to give it the symbol B. So again, carrier C, solute A, solvent B. Okay, so this is just a simple. Okay. So now let's talk more about the extraction process itself. How many types of uh, LLE process we have, or processes? Okay, LLE refers to liquid extraction. So how many types of this liquid extraction we have? We have many types. Mainly we are going to focus on three types, or let's say no, let's say two types mainly. The first type is, it's like distillation. First type is single stage liquid extraction. Single stage extraction. And the other type is multi-stage multi-stage liquid extraction. Okay, and under this category which is multi-stage extraction, we have two subcategories, which are cross current multi-stage liquid extraction, cross current multi-stage liquid extraction, and the other type is counter current. Okay, so again, liquid extraction process, we have many types. Two of these types are the single stage liquid extraction and multi-stage liquid extraction. This multi-stage liquid extraction has two modes. The first mode is cross current. The other mode is counter current. Okay, so mainly we are going to spend later, the next video are going to talk about single stage. The next one is cross current, and the last one is counter current. The most famous one out of these is the counter current multi-stage liquid extraction. Okay, but before we go to the next video that where we are going to discuss the single stage liquid extraction, we need to agree on some simples. Again. Okay, so the first thing, we know that distillation is just a column. It's a column. It is a tower, a long tower where you have the trees. But what's extraction unit? Extraction unit is simply a vessel. It's a vessel. It's a simple vessel. Okay, and in this vessel, if it is a single stage, you have one vessel. If it is multi-stage, you have more than one vessel, and that's it. As simple as this. Multi-stage, you have too many vessels. Single stage, you have one vessel. Okay, so let's agree on the simples that we are going to deal with. The first thing is the feed. We are going to call it F. Okay, the feed, we are going to call it F. And this feed, as we said before, it contains what? It is like, again, we go back to the example of oil, salt, and H2O. So the feed contains mainly oil and NaCl, or to be more general, it contains what? It contains carrier and solute. In other words, it contains C and A, as we agreed on the simples before. So you need to know this by now, that the feed contains mainly A solute and carrier C. The question here, could it contain some solvent B? Yes, maybe. Maybe sometimes it contains some of the solvent B. Why not? Sometimes, yeah. But it will be in very small quantities and traces in finite uh, quantities. Very small quantities. That's usually negligible. So we could have some of the solute, but mainly we will have in this feed the solute A and carrier C. Okay. And then we are going to feed the solvent. And the solvent stream, we are going to call it S. I'm going to call it S. Someone may wonder here, wait a minute, you say that solvent, we are going to call it B. So why you call the solvent S? The answer here, you need to be careful here. Why? S here represent that stream. S represent that stream. And this stream mainly contains the solvent B, but it could contain some traces of the solute or even some traces of the carrier. Why not? Okay. So again, to better illustrate the concept, uh, here, let's back to this one. Here, this stream, we call it feed F. But this feed, is it only one component? No, we said it is mainly A and C, solute and carrier, and sometimes you can have some small amounts of the solvent B. Okay, so you need to distinguish here between stream and component. Stream and component. Stream could contain more than one component. Again, stream could contain more than one component. Okay, for example, this feed stream contain mainly A and C, solute and carrier. Similarly, this solvent stream mainly contains B, which is the solvent, but is it always the case? No, sometimes it contains some traces or small quantities of A or even C. Okay, so that's why we feel the need to call this stream as a whole stream to call it S. But as individual component, it contains mainly the solvent component that could be sometimes 100% B, 100% solvent, or sometimes, I don't know, for example, sometimes 99% B, and for example, 100% A. It could, okay, it could be the case, okay? So again, stream is different than component. One stream could contain more than one component. Okay. And then what happened? You mix these two together, the feed and the solvent. You mix them together, so you will have inside this vessel, you will have a mixture. You will have a mixture. So let's call this mixture M. Let's call this mixture M. Okay. And then after some time, you will get two outlet streams. Two outlet stream. Again, if we go back to the example of oil, NaCl, and H2O, H2O will attract this NaCl, so you will get H2O and NaCl and mainly oil alone. Okay, so in other words, what happens? Solvent attract the solute, and then you're left with the carrier. Sometimes they call the carrier the raffinate. Yeah, they call it raffinate stream. So this this raffinate stream, we will call it, let's say this one is the raffinate stream, so we will give it a simple R. We will give it a simple R. And the other stream, we will call it extract. So to better illustrate the concept, we have this vessel, we have feed stream, and we have solvent stream. Then we have the output as extract stream and raffinate stream. Again, this feed contains mainly solute and carrier, in other words A and C. This solvent contains mainly B, and it could be some finite small quantities of the other components. And then this extract, what happens, this B will attract the solvent A, so this extract contains mainly A and B. Okay, and then this raffinate contains mainly C, the carrier. Okay, so we can go back here and say that this extract contains mainly A and B, solute and solvent, and this raffinate contains mainly C. But again, sometimes it's not only C, it could be the case, for example, 98% C, and I don't know, for example, 2% B or 2% A. Okay, but mainly it is C. So as we said before, E extract is a stream. A and B are components. Again, R is stream, but C is a component that mainly composed of raffinate, mainly composed of the component C, the carrier. Yeah, so that's it. Now let's give some samples for let's give some samples for composition. It is like let me remind you, with distillation, we said here we have a feed and we have the composition ZF, and then we have the distillate with the composition XD, and then we have a waste with the composition XW. And as you know, this composition of the feed or composition of the distillate or composition of the waste are for which one? Let's say the feed is a binary mixture of A and B. So as we said before, mainly we are going to refer all of this composition by default to the more volatile component, which is A. So when we say ZF, we mean here composition of A. Composition of A in feed stream, and again when we say XD, we mean the composition of A on the distillate stream. Again, when we say XW, we mean the composition of component A in the waste stream. So again, F feed is a stream, A is a component, ZF is a composition of A on the feed stream. Again, D is stream, A is a component, XD is the composition of this A on that stream, which is distillate. Yeah, and again, XW is composition of A, which is a component, in stream W, which is a stream. Okay, so we can write a quick or we can draw quick drawing again for extraction process. So for extraction process, we have what we have here. This is the feed with composition of A X feed, and we have here solvent S with a composition XS. Then they get mixed. We have a mixture here with a composition XM of solute A. Then we have two products, top products, which is it doesn't have also to be top product, but just for convenience, we are going to do it as a top stream. here extract E with composition of extract XE, and then we got raffinate R with a composition XR. All of these composition referred back to solute A. Okay, solute A, this composition, and this one XF, XS, XE, XR, all are for solute A. So XF is composition of solute A in feed stream. XS is composition of solute A in solvent stream. XE is composition of solute A in extract stream. XR is composition of solute A in raffinate stream. Okay, so now we can perform a material balance that we are going to need it later. So let's look at the overall system and then write material balance. We know that accumulation is equal to input minus output plus generation minus consumption. And we don't have chemical reaction here, so they are zero, generation and consumption. And assume a steady state process, so accumulation is zero, so you end up with N equal to out. Okay, so let's look at the overall system. So what's the inlet and outlet? We have two inlet, F and S, and two outlet, which are E and R. These could be molar flow rates or mass flow rates, but usually when we deal with extraction, we prefer to deal with mass flow rates, usually. But it doesn't mean that you are not going to deal with the molar flow rate, but it is usually you deal with mass flow rates in extraction. So let's do this in equal to out. So F plus S equal E plus R. And if you want to do component, so this is overall material balance. Now, if you would like to do a component material balance on component A, for example, which is our focus solute, so this simply will be XFF plus XSS, this is XS, equal to XEE plus XRR. Okay, so that's it. This is material balance on the overall system. Now suppose you want to do material balance on subsystems. For example, you want to do material balance only on this system, or you want to do material balance on this system. Let's start with this system. So simply you have F plus S equal to M, right? And if you would like to focus on this system, so you have what? You have this M equal to E plus R. So usually I like to write it in this way. F plus S equal to M equal to E plus R. So let's read it together. Feed plus solvent will be mixed to form a mixture inside the vessel. Then you will get two streams. One is the extract and one is the raffinate. This is the overall material balance, and similarly you can write component material balance. So XFF plus XSS gives you XMM, gives you XEE plus XRR. Yeah, that's it. So this is the material balance, and we are going to need this material balance later. Okay, we are going to need it later. Okay, another thing that I would like to mention here before we end up with this video is that remember, in distillation you have two phases, right? You have vapor phase and you have liquid phase, and within this vapor phase you have A and B. Within liquid phase again you have A and B, and the composition of the vapor phase, remember, we called it Y, and composition in the liquid phase we called it X. and this x and y, they are referred to by default to A, which is the more volatile component. Okay, so when we just say y and x, y means composition of A in the vapor phase, x means composition of A in the liquid phase. Then we can represent it graphically using this graph. If you remember, x and y graph, where you draw 45-degree line, and then you draw equilibrium curve between x and y. This diagram, we call it vase diagram. We call it vase diagram. We call it vase diagram. Okay. Yeah, this diagram, we call it a vase diagram, which is nothing but a simple diagram that's drawn between composition in one vase and composition of another vase. In this case, for distillation, they are composition of liquid vase and vapor phase. Now, similarly, in extraction, can we have a vase diagram? Yes, we can. We can have a vase diagram. Again, this vase diagram is based on component A, which is the solute in this case. In this case, it is the solute for extraction. So again, but the problem here, do we have vapor and liquid? No. Here we have a liquid and liquid. Okay? So we need to draw this diagram between two vases. But what are these two vases? Simply they are extract and raffinate vases. See these two vases, extract and raffinate. So you have what? You have extract vase and you have raffinate vase. We don't have here liquid and vapor. No, we have liquid and liquid, but they are two different liquids. Remember the example of oil and water. When we say water is heavier, so it will go down. Oil is lighter, so it will go up. Same thing applies here. Okay, we have an extract and raffinate. This raffinate with the composition XR, and this extract with the composition XE. Again, these two vases, these two compositions are referred to solute A. Solute A. So we can draw same diagram, but instead of X and Y, we will draw it between XR and XE. Raffinate composition and extract composition. And again, we can draw our 45-degree line, and then we can draw the equilibrium line, which is, instead of being between X and Y, it will be between XR and XE. Composition in raffinate vase and composition in extract vase. Okay, so this is again what we call it vase diagram between two vases, raffinate and extract. Okay, so this is one diagram. Another famous diagram, it's new to you I think, is called components. So this is the second one, components diagram. This diagram is drawn between the three components. We have, remember, we have a ternary system. We have a ternary system where we have three components. We have three components which are, so again we have two vases, extract and raffinate, but we have three components which are A, B, and C, as we said before. A is solute, B is solvent, C is carrier. Okay, so can we draw this component diagram? But wait a minute, what do you mean by a component diagram? Component diagram is simply a diagram that shows the composition of each of these three components, their compositions. Okay, so as you can imagine, we need how many axes, how many components we have here? 1, 2, 3. So we need 3 axes. We need 3 axes. Let's call them x, y, and z axis. Okay. So let's say randomly. Let's say randomly, or yeah, let's say arbitrary that x is let's say arbitrary that x is a composition of vase, for example, A represent composition of vase A, and Y represent a composition of vase B, and Z represent a composition of vase C. Okay. Okay. So it happens here at this point, the origin, you have 0A, 0B, 0C, and then as you go along the x-axis until the end, you reach a point of 100% A. So this is from 0% to 100% A. This is the x-axis. Similarly, the y-axis is from 0% Y up to 100% B. So this is along the y-axis from 0% B to 100% B. Similarly, along the z-axis from 0% C to 100% C. Okay. So this is called what? This is called components diagram. But there is a problem here. There is a problem. The problem here is that this diagram is not like the vase diagram. See, the vase diagram here is two-dimensional diagram. But here the component diagram is a three-dimensional diagram where you have x, y, and z. In other words, one axis for A, one axis for B, and one axis for Z compositions. Okay? The problem here is this is a three-dimensional diagram, and the vase diagram is two-dimensional. So the question here, is there a way to represent the components diagram in a two-dimensional form? Can we represent this diagram in a two-dimensional form rather than this complicated three-dimensional diagram? The answer is yes. Mathematicians has came up with a brilliant idea, which is the triangular diagrams. The triangular diagrams, which has mainly two types. This two-dimensional diagram, it could be equilateral diagram, or it could be upright diagram, upright triangular diagram. Okay, as you can see, these diagrams are two-dimensional. They are not three-dimensional, they are two-dimensional. So it could be equilateral or triangular, upright triangular diagram. Again, it could be equilateral triangular diagram or upright. Upright means 90 degree triangular diagram. In this course, I'm going to focus only on this type, which is the upright. Of course, both, whether you use the upright triangular or equilateral triangular, both will give same answer. Later when we analyze extraction problems, both will give you the same answer. But I feel this is simpler to discuss. This is simpler to understand in upright triangular diagram. So I'm going to focus on this type of diagrams. Okay. So what this diagram is, simply It is, you draw this 90 degree, you draw this 90 degree triangle. Oh, let me draw it like this. We draw this 90 degree triangle, and again, same idea, same idea. This is x-axis, this is y-axis, this is z-axis. But rather than having them in a three-dimensional form, no, we draw it in a two-dimensional form to be easier to analyze and solve problems. Okay, so let's say this is the origin, this is the origin. How many corners we have here in this upright triangle? We have three corners. 1, 2, 3. Three corners. Okay, so let's call this corner corner C, refer to component C. And then let's call this corner corner B, refers to component B. And then let's call this corner corner A, refers to component A. So let's link to the three-dimensional diagram. In the three-dimensional diagram, we said from here to here is from 0 to 100% composition. And similar from here to here and here to here, or from 0 to 100% composition of a given component, A, B, or C. Similarly here, at one of the corners, any corners represent 100%. A, in this corner, it is 100% C. In this corner, it is 100% B. In this corner, it is 100% A. So you can have this scale. You can have this scale. If this is 100% B, so this is 0% B. So from here to here, it is from 0% to 100% B. Okay? And similarly, if this is 100% C, so from here to here, this is 0% C, and this is 100% C from here to here. From here 0% C, and here 100% C. And similarly, you can extend the idea. So similarly, from here 0% A, and here 100% A. And in between you can have, I don't know, 10% A, 50% A, up to all the way to 100% A. Okay? And vice versa. And vice versa. I from here is 0% C, and here 100% C. So this would be 10% C, I don't know, any 50% C, all the way until you reach this corner where you have 100% C. And same idea applies here. From here to here, 0 to 100% B. From here to there, 0 from 100% A. Okay, so this is how to understand this upright triangular component diagram. Okay, so this is your axis. Again, you would have this three axes. One of the corner represent 100% C, this is 100% B, this is 100% A. To be consistent, we will always call this corner C, and we will always call this corner B, and we will always call this corner A. Okay, so this is our axis. Then to draw the equilibrium curve inside it, you needed some data. You need the data. Okay, you need the data of composition of A, composition of B, and composition of C. you need to have this set of data. It is like when you have in distillation, you have X and Y data, and then you draw them in XY diagram. Similarly here, you need to have composition data of A, B, and C, and then you can draw them on this triangular diagram. Okay, so it is easier if you want to draw a point. I suppose you have a point XA equal to 0.1 and XB is equal to 0.2 and XC is equal to 0.7. So it is easier to look at, don't look at this axis, look only at these two axes to make things simple. This axis represents 0% B up to 100% B, and this axis represents 0% A up to 100% A. Okay, so what you will do, let me do it again. This is C, this is B, this is A. So suppose you have a composition that we said 0.1A, which is 10%, and 0.2B, which is 20%. So you don't have to look at C, don't look at this axis. Okay, so what you will do, you will look, where is 10% A? It is somewhere here, because here is 10% is 100% A, here 0% A, in between is, let's say, closer to 0, this is 10% A, this is 10% A. And then where is your B? Here this is 0% B, here 100% B, so 20% B would be somewhere here. Somewhere here is 20% B. This is 20% B. Okay, so this is your point. This is your point. Okay, so you don't have to look at C composition. You can draw your curve, equilibrium curve, only by looking at XA and XB. Okay, so you can think of this diagram as simple as this, as a diagram, as a two-dimensional diagram, where you have here composition from 0 to 100% B, and here from 0 to 100% A. And then you can draw your points and then connect them to have the equilibrium curve. And similarly on the vase diagram, to draw this vase diagram, you need to have equilibrium data between composition of A on the raffinate vase and on the extract vase. Then you draw the point and then you connect them, and that's it. So this is how to develop these two diagrams. So to summarize what we have discussed, we discussed the LLE, the liquid-liquid extraction, and then we discussed the material balance, and then we discussed the vase diagram, which is something like this, and then we discuss component diagram. We discussed component diagram, which is something like this. Okay, in the next video we are going to talk about the first type, which is the single stage liquid-liquid extraction. Thank you for your listening, and I wish you all the best.